Welcome to this comprehensive tutorial on support vector machines, or SVMs. In this video we'll explore the basics of SVM, a powerful machine learning tool for classification and regression tasks. SVMs have gained popularity for their ability to handle complex data and deliver high accuracy, often rivaling neural networks. Whether you're a student, researcher, or professional, understanding SVM will enhance your ability to tackle pattern recognition problems. Let's begin by setting the stage with a brief overview of machine learning and the role SVM plays in this exciting field. Machine learning is a branch of artificial intelligence focused on developing algorithms that enable computers to learn from data. Rather than being explicitly programmed for every task, machines use these algorithms to identify patterns, make predictions, and improve over time. Machine learning overlaps with statistics, drawing on mathematical foundations to create robust models. Over the years, various techniques have emerged, each suited to different types of problem. SVM stands out as one of the most effective tools for supervised learning, especially when dealing with classification and regression. Support vector machines were first introduced in 1992 by Bozer, Guyon, and Vapnik. Since then, SVMs have become a cornerstone in the machine learning community, especially for tasks involving pattern recognition. Initially popular among researchers, SVMs quickly gained traction due to their impressive performance in tasks like handwriting recognition. Their ability to generalize well and avoid overfitting made them a preferred choice for many applications. Today, SVMs are widely used in fields ranging from image analysis to bioinformatics. At its core, a support vector machine is a supervised learning model that can be used for both classification and regression. SVMs work by finding the optimal boundary, or hyperplane, that separates different classes in the data. This boundary is chosen to maximize the margin between the classes, ensuring that the model generalizes well to new, unseen data. By leveraging concepts from optimization theory and statistical learning, SVMs offer a robust framework for tackling complex problems. Statistical learning theory provides the foundation for SVMs. It addresses the challenge of making predictions and decisions based on data. The theory guides us in choosing a model that best represents the underlying function in the target space. In supervised learning, we're given a set of labeled data and aim to find a function that minimizes the expected error on new, unseen data. This approach ensures that our model not only fits the training data but also generalizes well to future cases. Early machine learning algorithms focused on fitting the training data as accurately as possible. However, the true test of a model is its ability to generalize, correctly classifying data it hasn't seen before. SVMs excel in this area, often outperforming neural networks by avoiding overgeneralization. The key is finding the right balance between model complexity and the number of training epochs. This balance ensures that the model is neither too simple nor too complex, leading to better performance on real-world data. Neural networks have long been popular for supervised and unsupervised learning, offering flexibility through architectures like multi-layer perceptrons. However, they come with challenges, such as determining the optimal number of neurons and dealing with local minima. SVMs address some of these issues by providing a unique solution and maximizing the margin between classes. This makes SVMs particularly attractive for tasks where clear separation between classes is essential. Imagine plotting your data and trying to draw a line that separates two classes. There are often many possible lines or hyperplanes that can do this, but which one is best? SVMs solve this by selecting the hyperplane that maximizes the margin, the distance between the closest points of each class. This approach not only improves classification accuracy, but also enhances the model's ability to generalize to new data. Maximum margin classifier is a core idea in SVM. By maximizing the distance between the hyperplane and the nearest data points from each class, SVM ensures that the model is robust to small changes in the data. This means that even if there's a slight error in the boundary's position, the risk of misclassification is minimized. The maximum margin approach also helps avoid issues like local minima, which can plague other algorithms. Let's look at the mathematical side of SVM. The goal is to find the hyperplane that separates the data with the largest margin. This involves solving an optimization problem, where we minimize the norm of the weight vector while ensuring that all data points are correctly classified. The solution requires quadratic programming and introduces concepts like Lagrange multipliers. The result is a model that is both powerful and mathematically elegant. SVM hyperplane can be represented mathematically by equations involving the weight vector and bias. For each data point, the model ensures that it lies on the correct side of the hyperplane with a margin of at least 1. The closest points to the hyperplane are called support vectors, and they play a crucial role in defining the boundary. By focusing only on these support vectors, SVM achieves both efficiency and accuracy. Support vectors are the data points that lie closest to the decision boundary. These points are critical because they directly influence the position and orientation of the hyperplane. If you were to remove a support vector, the optimal boundary could shift. This property makes SVM sparse, as only a subset of the data points, those that are support vectors, are needed to define the model. Real-world scenarios, data is rarely perfectly separable. Outliers and noise can make it impossible to draw a clean boundary. SVM addresses this with the soft margin classifier, which allows some data points to be on the wrong side of the margin. By introducing slack variables and penalizing large deviations, SVM finds a balance between maximizing the margin and minimizing classification errors. This flexibility makes SVM robust to imperfect data. Not all data can be separated by a straight line or hyperplane. The kernel trick is a clever technique that allows SVM to handle nonlinear boundaries. By mapping the data into a higher dimensional feature space, SVM can find a linear separator in this new space, even if the original data is not linearly separable. The kernel function computes the inner product in this feature space without explicitly transforming the data, making the process efficient and scalable. Kernel functions are at the heart of the kernel trick. They enable SVM to operate in high-dimensional spaces without the computational burden. Common kernel functions include polynomial, Gaussian radial basis, exponential radial basis, and multilayer perceptron kernels. The choice of kernel depends on the problem at hand, and selecting the right one can significantly improve model performance. Experimentation and cross-validation are often used to determine the best kernel for a given dataset. SVMs are powerful, but their performance depends on controlling model complexity. Parameters like the kernel type and regularization factor influence how well the model generalizes to new data. Too much complexity can lead to overfitting, while too little can result in underfitting. Cross-validation is a practical approach to tuning these parameters, ensuring that the SVM achieves the right balance for the task at hand. SVMs are widely used for classification tasks. The process involves training the model on labeled data where each instance has a known class. The SVM learns to separate the classes by finding the optimal hyperplane. Once trained, the model can predict the class of new unseen data based on its attributes. Feature selection is often combined with SVM to improve accuracy and interpretability, especially in high-dimensional datasets. Beyond classification, SVMs can also handle regression tasks by modifying the loss function. In regression, the goal is to predict a continuous value rather than a class label. SVM regression models use techniques like the epsilon-insensitive loss function and kernel mapping to fit both linear and nonlinear relationships. This versatility makes SVM a valuable tool for a wide range of predictive modeling problems. SVMs have found success in many real-world applications. They are used for text categorization, image classification, handwriting recognition, and even medical decision support. The ability to handle high-dimensional data and avoid overfitting makes SVMs especially useful in fields like bioinformatics and information retrieval. Choosing the right kernel and optimization strategy is key to unlocking the full potential of SVM in these diverse domains. SVMs offer several strengths. They are relatively easy to train, avoid local optima, scale well to high-dimensional data, and allow explicit control over model complexity. However, they also have weaknesses such as the need for a well-chosen kernel function and potential challenges with very large datasets. Understanding these trade-offs helps in deciding when SVM is the right tool for your problem. Summary: support vector machines are a powerful and versatile tool in the machine learning toolkit. They combine strong theoretical foundations with practical performance, making them suitable for a wide range of tasks. As research continues, new developments in kernel design and optimization promise to make SVMs even more effective. Whether you're working on classification, regression, or other predictive tasks, understanding SVM will give you a valuable edge in data modeling.